Now we'd like to consider the conditions for the gravitational instabilities. When we discuss the formation process of stars, we considered gravity and pressures. Now we examine the stability of gas in a disk. In addition to gravity and pressures, we need to consider the tidal force. When some object is making a rotational motion, tidal force is acting on this object. Tidal force is a difference of the centrifugal force and gravity of a central stars. So in the outer edge, tidal force is acting because the centrifugal force is larger than the gravity. In the inner edge, gravity is larger than the centrifugal force. Net force is directed toward the central stars. So tidal force prevents gas from contracting to a single point, so like pressures. So gravity makes a gas to contract. On the other hand, pressure and tidal force prevent gas from contraction. So we need to consider these three. If the gravity is larger than the sum of the pressure and tidal force, then gravity makes the gas to contract and the gas is accumulated in some point. So we call such a situation is a gravitational instabilities. If the perturbations makes more material accumulated in these regions, if the gravity is larger than the sum of the pressure and tidal force, density is increasing. And then finally, this becomes a really high dense region. Low dense region, high dense region. So this might be the seed of some dense object in a disk. If the gravity is smaller than the sum of the pressure and tidal force, even if some gas is accumulated in some region, pressure and tidal force prevent the gas to contract. Instead, the increased density decreases by the pressure and tidal force. So we'd like to find out the conditions for the gravitational instability in this section. At first, we'd like to consider perturbation. So assume a part of the disk is compressed. So we consider cylinder region with the radius of the r and the height of the 2z. r is compressed to the r minus z. Then calculate the volume variations. Change of the volume can be calculated after the compression. Areas of the cylinders pi times r minus g squares minus pi r squares, and the height of the cylinders 2z. If you consider r is much larger than z, this can be approximate minus 2 pi r z times 2z. Initial volume can be calculated pi r squares times 2z. So these equations can be minus 2 z over r times v. So from this equation, you can find that delta v over v can be expressed minus 2 z over r. So this is the volume variation. Then practice 6.4. Obtain the relation between the volume and pressure variations in the isothermal conditions. Isothermal condition is a constant temperatures. So we consider the equation of state Pv equal nkt. So temperature is constant. So this means delta T equal to the 0. So this means delta Pv equal to the 0. So from this equation, P delta V plus V delta P equals 0. So from this, you can find that the delta P over P equal minus delta V over V. Volume and pressure variation is related with this equation. Then we have a delta V over V is minus 2 z over V. Also we derive delta P over P is minus delta V over V. So from the second equation, you have this equation. Using the first equation, we have this relations. From this equation, you can find delta P is equal to z over r times P. So using this equation, we could find that the pressure gradient is expressed F sub P equal 1 over rho, round P round r. So we use the order of estimate 1 over rho delta P over r. Pressure gradient can be estimated 2 times z over r squares times P over rho. This is the pressure gradient. Then we'd like to estimate tidal force. So tidal force is the difference of the centrifugal force and the gravity of stars. Then centrifugal force can be estimated r plus r times omega squares. This position has a omega r plus r minus z. So this could be expressed gm sub stars over r plus r minus g cube. So you can substitute this omega is here. You can change this equations. Gm sub stars over r plus r squared times 1 minus Guji over r plus r minus 3. So this becomes Gm sub stars over r plus r squared 1 plus 3 Guji over r plus r. Also, we could calculate the gravity of the stars using this equation. The tidal force at this position, we can estimate the difference of the centrifugal force and the gravities. The centrifugal force is larger than this 3 Guji over r plus r. So in this approximation, we use a capital R much larger than the r. The tidal force is estimated with this equation. Then self-gravities, we consider some region is compressed by Guji. Originally, cylinder has a radius of the r. Is compressed by amount of the Guji. Outer gas is entered this cylinder from this region. So this r plus Guji. This gas enters the cylinder and increase its mass. Then gravity becomes stronger. So we need to estimate the increase in the mass. The mass in the shaded regions can be estimated. Pi r plus Guji square times 2g is a height times the density of low minus original cylinders. Pi r square 2g is a volume of cylinder times density of low. Then the r is much larger than the Guji. Then this is approximated 2 pi r Guji 2g low. 2g times low, this corresponds to the surface density of the sigma. So increase in mass is estimated 2 pi r Guji sigma. So increase in the self-gravity is due to the increase in the mass is minus pi g sigma 2 Guji over r. When the pressure gradient, tidal force, and the self-gravity becomes positive quantities, repulsive force is acting on the accumulated gas. Then it's returned to the original stable state. But if the total sum of the three forces is negative quantities because the gravity is stronger, then gravity tries to attract the more gas, then density is increasing. So this mode is correspond to the unstable mode. For the unstable mode, gravity is stronger than the sum of the pressure and tidal force. Then you can substitute. Gravity is in the right hand side. And the sum of the pressure and tidal force are given in the left hand side. We consider perturbation wave. This is a lambda wavelength. And actually this is 2r. Sometimes we use wave numbers instead of the lambda. K is defined 2 pi over lambda. Then 4r equal to the lambda. So r is lambda over 4. Instead of the lambdas, if you use a k, r is expressed pi over 2k. Then look at this equation. Pressure, tidal force, gravity, all terms has Guji. So Guji is going to be cancelled out. And this is equal to the omega squares. P over rho is square of the sound velocity. Instead of r, if you use k, it becomes this equation. When this condition is satisfied, gravity becomes stronger than the sum of the pressure and tidal force, lead to the gravitational instability. First term, the left hand side corresponds to pressures. This term corresponds to tidal force. This term corresponds to gravity. For small k, so this means large lambdas. This equation cannot be satisfied because to satisfy these equations, k have to be larger than the constant value of the omega squares. This cannot be satisfied due to the tidal force. Tidal force prevents the contractions. For large k correspond to the small lambdas. Pressures prevent the contractions of the gas because the first term, the left hand side, becomes larger than the right hand side. This condition cannot be satisfied for the large k. Condition can be converted. If k is a function of k, is 8c squares over 3 pi squares k squared minus 4g over 3 sigma k plus omega square is less than 0. Then we'd like to change this function of the fk. Then we'd like to draw the fk. The horizontal line is a k. The vertical line is a fk. Then if you substitute the k equals 0, omega squares. This is omega squares. Then axis given by these numbers, so pi squares g sigma over 4c squares. The minimum value is given by this equation. So omega squares minus pi squares over 6 g squares sigma squares over c squared. So Fk is given by parabolic equation. So condition for the instability is given by this equation. Fk is a negative quantities. This region is an unstable mode. So this means these values need to be the negative quantities. So omega squares minus pi squares over 6 g squares sigma square over c squares need to be negative quantities. So from this equation, you can find the square root 6 c omega over pi g sigma need to be less than 1. So c is sound speed, omega and sigma are function of the distance from the central stars. If the sound speed and omega and sigma satisfy these equations, the gas becomes unstable gravitationally, and we derive the conditions for the gravitational instabilities using the very simple models. Okay, this is it for the second lectures for the gravitational instability.